Now, I'm going to go through this test. There are two tests. What I'm going to go through is the 8. I'll go through first problem A, first problem B, and so forth. They're very similar, but different enough because of problems. All right, here, first, you all see this here? All right, so the whole idea is this. That this is for test A. Let me see if I can reduce that. I don't believe anybody might have 140 out of 40, but I might be wrong. I remember 37, but I do know that we had several very high grades, I mean nearly perfects, and then we had a bunch of people where they literally left problems blank, and I'm just going to call that a time thing. That's where the 10 points came. Sorry about this. I got the mic on. Give me a second. All right, for this problem, this is the first one in test A. Let me go through this with you, and I'll put these up there for everybody, and I'll put them on your web page. So for this one, I've got a frequency of 10 megahertz, vertically polarized, and it says the reflected wave is 20 volts per meter. It gives sigma 0.01 and epsilon relative 3 over here. Now, when a couple people, because there was a problem in the other test, if you use these values because they were printed there, I give you full credit. There was some confusion. But anyway, going down here, first thing you got to do is get the intrinsic impedances of the region. Since I came from air over here, that's just 120 pi. Here I have to calculate it, so that's what I did here. I called it A to 2. And it's just j omega mu naught omega over sigma plus j epsilon relative epsilon naught omega. It's straightforward. We've done this a lot of times. So after you get that, magnitude and angle, or you could leave it as in rectangular. After that, the next thing you had to do is get the reflection coefficient. That's just A to 2 over A to 1. I'm using just capital T here because the gamma function that I have, if I put it in there, it's a lot of keys I've got to press, additional keys. So this is the reflection coefficient. Now, I know the reflected wave divided, or the incident wave times the reflection coefficient is the reflected wave's magnitude. And I only cared about magnitude, not phase. Therefore, if I take the reflected wave by gamma, I get the incident wave. So that's my incident field right there. Just magnitude is all I care about. It was not meant to be a hard test in any way. These are straightforward things. Your calculators, you get eta 2, you calculate gamma because you have eta naught, it's 120 pi. Then after that, you get the incident electric field. Now, the transmission coefficient is 1 plus gamma times the incident field. It's just tau is either 2 eta 2 over eta 2 plus eta 1, or just 1 plus gamma. Do you all follow me on this class? There were people that didn't have a clue how to do this one. It troubled me. Because this is very important. This is something you have to know where we're going. If you can't do this, you're in real trouble. So now once we have this, we get the transmitted field into region 2 is just going to be 1 plus gamma times the incident field, or this is E transmitted. After that, P transmitted here is 1/2 E transmitted squared divided by magnitude of eta 2, and people forgot this, a lot of people forgot this, times the cosine of the angle of eta 2. You all follow me on this? Remember the cosine of the angle? It cost people a point. A lot of people did not put that in there. Does everybody follow me on this class? You have to have that cosine in there. And if you did 1/2 E, real part of E cross H conjugate, you had that automatically in there. But people didn't, I only know of a few people that used that formula. After that, coming down here, what else? The reflected power. Here you don't have a cosine because the angle for eta naught is 0. So it's 1/2 E relative, the reflected field squared divided by eta naught. And that's the P reflected. So these are the answers right here for the first test. They're straightforward, and I'll put these up. I'll put it on your, I'll put it on OneNote for your test 1 solutions. Okay, you can check if I made a mistake, bring it to me. That's test A. Test B, over here. The only difference is that the value of sigma and epsilon relative was different. If you use the ones down here, I should have given you full credit. All right. I mean, I think it was 3 and 0.01 here. It was the prior values. If you use those values and you got it right, and I marked it wrong, come see me. I thought I went through that carefully, but I may have made a mistake. This one's straightforward, same thing again. First you have to get A to 2. After you have A to 2, then you have to get the reflection coefficient. After you have the reflection coefficient, you divide the reflected field by the reflection coefficient to get the incident field. After you have the incident field, you get the actual power you can go ahead and get the transmitted field as 1 plus the reflection coefficient, right? That's tau, times the actual incident field is the transmitted field. That's here. Once you get the transmitted field, the transmitted power is 1/2 E transmitted squared over eta squared. And by the way, it's magnitude of E transmitted, magnitude of eta, times the cosine of the argument of eta 2. And that's what you should get, all these things. So the answers are here to look at, and I'll post them, all right? And that was not meant to be a hard problem. It was actually a problem I pulled from a quiz. I don't know if you know this. I changed a few values, but do you all remember this from a quiz class? All right, it was just a quiz problem that I pulled. That's all it was. All right, and I think I did one thing, though. I think I gave you the reflected, not the incident field. On the quiz, I gave you the incident. That's the only difference. If you know what you're doing, you can work backwards. All right, second problem in test A. This is the waveguide. It's giving you a waveguide. It's got dimensions. A is 2.5, B is 1, a length of 9 centimeters. It's fed by 100 volts at 8 gigahertz. It's connected to a load of 400 ohms. Determine the corresponding wavelength in the guide. Goes through this. Wavelength in the guide, the mode, the group velocity in the guide, the input impedance of the waveguide. Now here's where this is the problem. That shouldn't have been there, but it was. So if people got confused in that and used an RS of 100 ohms or an RL of 100 ohms, I tried to accommodate that. It was meant to be the Z load here was 400 ohms. This is from a homework that I posted. So it was meant to be 400 ohms. First thing you have to do in this problem, and this is for test A, is you're going to have to calculate the characteristic. First you have to calculate the cutoff frequency. So the cutoff frequency for this one, for the 1 ohm mode, is 6 gigahertz. We're operating at 8. The next cutoff frequency after that is 12, and the next one after that is 15 gigahertz. So it was only one mode. It was the TE10 mode. Most of you got that right, and that's good to see. Once you realize it was the 1 ohm mode, the next thing you had to do is find that factor K, right? K is 1 minus square of FC over F squared. Some people inverted that. They had F over FC, I think. There was all sorts of mistakes on here. I couldn't figure out what you were doing because I just saw K in a number, and I didn't know how you calculate it. And that's another thing. Let me just say this. If you're doing this, if you want me to understand what you're doing so I can credit you with at least the right thoughts, you have to show the mathematical steps in logical order. If I see a scratch here and a scratch here and 2 values for K, I can't give you anything. Help me out and just be very logical in the way you lay it out. Yes?
How did we know it was 1 ohm mode?
I couldn't hear. What did she say? What?
So how did you know it was 1 ohm mode?
Well, what is the cutoff frequency for the lowest order mode? It's the 1 ohm mode, right? The cutoff frequency is what? 6, isn't it? Do y'all see that 6, kid? Well, it's operating at 8. 8 is above 6, so it will operate in the 1 ohm. The next one above that is where? 12, right? We're not above 12, so it will never get that mode. It'll never be a 2 ohm mode. It'll just be the 1 ohm mode. Everybody follow me on this class? I mean, most people got that part. I'll say that. After that, since it's 1 ohm mode, I calculate the value of K here. I get 0.661. Next, I get beta in the guide. And this is really omega times square root of mu epsilon times K. That's beta in the guide. And then I get the actual wavelength in the guide is 2 pi over beta in the guide. There are a lot of different formulas to get this. I'm going to tell you, you can actually take the wavelength itself divided by K, free space wave. You can get this a lot of different ways. I'm just showing you the way I did it. And this is, yes, sir. I can't hear you. What? Yeah, I tell you, we're going to talk about that later. All right? But yes, right now I just want to finish this test. So I've got that. So I get wavelength in the guide. Now I get the impedance of the guide. Since it's 1 ohm mode, I know the impedance in the guide, that's right here. It's Z0 here. I know that's going to be eta naught over K. A lot of people got that right. Only a couple messed that up. But it wasn't meant to be hard. After I have that, next thing I get is the input impedance. Now, ZL is given, right? And I gave you this formula, by the way. I wanted to make sure that I said I'd give it to you. I gave it to you. The only thing you had to make sure is beta in the guide goes here and the length of the guide goes here. And that's the formula. It's just plug and chug. A lot of people, believe it or not, they put in ZL here. Now, for Z naught. In other words, they mixed them up. I'm not sure why. The only thing I can think of, it's probably exhaustion. And one other thing I'm going to tell you. I didn't talk to anybody else about this, but these are some thoughts. That home game with Mississippi State on Saturday, I think it tore a hole in your study habits. That's my thoughts. And I think Sunday was a recovery day because this test was not that hard. It was almost identical to a test I gave 5 or 6 years ago where the average was just about 3 times what yours was. I had an average of over 80, I think, on this one, but I can't be absolutely sure. The reason I'm saying this is because there were a lot of people that didn't look like you knew what you're doing from get-go. You were struggling, started scratching your head. This test was meant to be something, if you were doing the homework and doing it, you're going to just fly through it. I mean, it's going to be a thing like that. There was nothing here that was meant to be really tricky. It was all laid out based on homework and class discussion. I promise you that. There's nothing here that's tricky. Yeah?
So a big difference I saw between this and homework was homework wanted us to solve everything mathematically, and then this has numbers, and that was a big disjoint between.
Well, wait. A lot of the homework did have numbers, though.
Yeah, but the way solutions were worked out, the solutions.
They do it arbitrary constants, but I'm going to say this. I know where you're going with this. What I always tell people to do is work out everything in terms of the variables, A, B, C, D, whatever, till you get the final form. Then put in the values if you're going through a proof. Here, there weren't proofs. It was just a formula, get an answer. There was no derivations. Now, for derivations, you do that, but if you're getting the final value, you put in the values. And another thing, too, like your calculators store all sorts of information. Symbolic, you had all these equations, basically. I mean, symbolic calculators got them all. But if you don't know what FC is, it doesn't mean anything to you. You've got to know how to calculate. You've got to know what these things mean. And if you don't, then you're in trouble. Like the ZL business for Z naught. If you don't know what Z naught really means, it doesn't matter if your equation says it or mine, because you have no real understanding. So putting equations down doesn't do much for you. You should crank numbers. I'll give you more problems with final number answers if you want that, and I'll do that for you. But I didn't try to make this tricky in any way. So then that's the input impedance that you get. And if you left it in terms of rectangular, you got full credit too. I asked for polar. Do me a favor from now on, give me polar. I'll start taking a half point off if you don't. I want polar numbers there. And then after that, let's see. Oh, you got to get the reflection coefficient, ZL minus Z naught over ZL plus Z naught. Now that Z naught is the characteristic waveguide impedance. It's not the impedance of free space. Follow me, class? So that would be the Z naught we calculated for the TE10 mode. Everybody hear me on that? Don't make that mistake again. You'll see this kind of problem again. All right, now that said, so now we can get the input impedance and all that. And I said RS, the source resistance was 0. I said it's being fed by 20 volt. Sorry. I said it's being fed by, where is that? 100 volts. This is for test. I guess, is this test A 100 volts? 100 volts, right? Now, there's no source resistance, so you don't have to have Zn over Zn plus Rs times Vn to get the value of the voltage, or times V source to get the value of the voltage just inside the waveguide. Does everybody hear me on this? I took the source resistance out of the problem to make it easy. You've got the value of the voltage just inside the waveguide there. Do you all follow me? So what is that equal to? Well, that's equal to this. It's equal to right here. That right here, if you think about it, that's the source voltage. I'm just going to write this down to make sure everybody sees this, because there were people that really didn't understand what was being asked for, I think. If I have a waveguide like such right here, and then there's a load here, get a different marker. Try this one. And this is a waveguide of length L, and then there's a source voltage fed right into it. this source voltage, remember on this guide, this is at Z equals 0. This is the way we do these problems. We said Z equal to 0, that's where the load is, right? Down here, I'm at Z equals minus L, right? Remember this problem? Z equals minus L. Now the voltage anywhere in here, V of Z, is equal to V0 plus, and then it's going to be e to the minus j beta Z, plus the reflection coefficient e to the plus j beta Z. You all remember that? All right, now, what I gave you was this at Z equals minus L. Got it? I gave you 100 volts right there. No source resistance, so you don't have a problem, right? That means if I want V0 plus, I can say V0 plus is equal to e to the plus j, and this would be beta in the guide times L, plus the reflection coefficient times e to the minus j beta in the guide times L. That's equal to 100 volts. And then you solve for V0 plus. Do you all follow me on this? Now, a lot of people set up basically that equation, and I want to tell you this. This bothered me. This equation is something you set up. You solve for V0 plus. Do you all remember this? Right? And I said V0 plus is what? It's equal to 100, because that's the source voltage, over e to the j beta guide times L, plus the reflection coefficient e to the minus j beta guide times L. Now here's where the numbers got bizarre. You have this down right on your paper, and you have the wrong answer for V0. The only thing I can think of is you haven't worked with your calculators enough doing that kind of calculation, because that's not a tough one, right? That's only a couple of complex numbers divided into a real number. But I'm telling you, they had this down. They had the right answer. I mean, the right equation, the wrong answer. So please make sure you don't make that mistake. I think I only took off a half point. If I took off a full point, see me. All right? But you can't do that. You've got to make sure you get the right answer. After you have V0 plus, then they want the voltage at the actual load, right? That was one of the things I asked. Correct? How do I get the voltage at the load? Well, ask yourself that. What is Z at the load? 0, right? We put the load at Z equals 0. Do you all remember this problem? Huh? What'd you say? No, Z is the point. The point in the Z axis is at Z equals 0. Follow me? It's at Z equals 0. All right? Are you with me on this, class? So at Z equals 0, I know that this is the general equation, right? For any L, if L is 0, it's just going to be V0 plus 1 plus the reflection coefficient is the voltage at the load. Here's something else I saw, and I don't understand how. People get V0 plus right, and then they do this. That's wrong. All right? It's not the magnitude. It's 1 plus the actual reflection coefficient here times V0 plus is V load. And I just cared about the magnitude. If you gave me just the magnitude of VL, that's all I wanted. I didn't want the phase. Now, after that, the load is 400 ohms. It's pure real, right? After that, to get IL, the only thing I do is take VL magnitude over 400. And now I've got IL. Follow me on this? Now, the load was strict real, right? There's no imaginary part. You did not need to do 1/2 the real part of V times I conjugate. The only thing you wanted to do is power at the load here, right, would just be 1/2 magnitude of VL squared divided by 400, or 1/2, and it could be times magnitude of IL squared times 400. Either one of those two give you the right answer. If you want to do the 1/2 the real part of V times I conjugate, you can do that, but this is easier and quicker. And I saw a lot of things I wasn't sure about what you were actually trying to do to get that power. All right. Now, anyway, so this is what it comes down to. You can look at the mathematics. It's straightforward on this one. And you get these values, 0.057, 570 for the impedance. You get a group, I didn't say this, group velocity is equal to C, right, times K. Do you all remember that, class? Group velocity is less than the speed of light. A lot of put down the group velocity here as greater than the speed of light. That's an impossibility. V group is the velocity energy travels. Are you with me, everyone, on that? Okay. Let's see, that's Zn, and that's just punching the numbers into your calculator correct with the equation. The voltage at the load, after you calculate V0 plus, you get that. I at the load is this, and power at the load is that for this problem in test A. For test B, right here, these are the values for the, wait a second, was test B 100 too? Yeah, it's the length is 4.5 centimeters, not 9 centimeters in test B. That was the only difference. And you can check the numbers on this one. I've got the equations down and the answers. And and this is another thing. Now, I don't know if you ever care to look into this, but I use Emag10. You can download it free. And it's what you see is what you get. I'm going to say this. The only thing you can't do with the free version is get the argument of a complex number, but most of that stuff is easy to get. Just magnitude is the only thing I care about. Emag10, the free version, will do everything I'm showing you on this thing except the arguments where I get the angles, all right? And it's the thing I like about it. I don't get nothing for telling you this, but the thing I like about it, it's what you see is what you get. Not like MATLAB where you put a lot of equations in and have to execute it. As soon as you plug them in, they execute. You change one number, it changes everything. So it's real nice for professors if you want to make up problems with the same basic form of doing it, but different final answers. You change a few things at the very beginning and everything changes accordingly. Now, I'm going to tell you one other thing about Emag10. It saves me a lot of time. I know you need to use your calculators, all right? I'm very aware of that. Your calculators probably do a lot of symbolic stuff too. I don't know how powerful they are because I don't have one. I have an old HP from about 30 years ago that I use when I need a calculator. I'm not kidding. It does everything I need. But Emag10 allows you to go quickly through homework. I'll tell you that much. Much quicker than MATLAB or your calculator, in my opinion. And if anybody wants to challenge me on that, see me after class or after 2 o'clock today. Yeah.
Is it free?
Yeah. It's called PTC Emag10. I believe Emag10, M-A-T-H-C-A-D. How many have tried this before, Emag10? Anybody? You? 2, 3, 4?
So your concern is that on the test we're not accustomed to using our calculator with complex numbers. Why are you encouraging us not to use our calculators on homework?
What you're doing, you know what? You should work for CNN. I mean, what I'm trying to do is this, all right? I'm trying to say if you want to work problems and get the answers like this, and a whole bunch of problems, not just the homework problems, but a bunch, this will do it for you. You can change numbers very quickly. Your calculators you're going to need for this, the basic stuff to check, but this will get you the right answer quick. You can verify it in your calculators. All right? But I did want to say one other thing too. This business right here bothered me. From now on, make absolutely sure you can do this kind of thing. And here's something that troubled me. They had the right value for beta G. They even had the right equation. And then they got the wrong answers. So I'm figuring, how in the world can you have that equation down and punch the wrong numbers in unless you don't understand something about your calculators? And I don't know how to do this on all your calculators. But normally what I did when I was in your shoes, I would take this number and I would store it in memory. Then I would recall that number and divide it into the other one. I would always have like beta guide times L, separate memory. Then anything I wanted to do that, I'd recall that memory and execute that thing. Something else I'm going to say too. I don't know what it is, how you guys do this, but see, beta times L is in radians. And if your calculator's in degrees, you're in trouble. I work in radians almost all the time unless it says degrees and then I change it to radians. Now please, I don't know the mistakes that were made, but I'm smelling things like radian problems to degrees. I think sometimes people mess up with this division somehow, and I don't know what you're doing, but it's getting a very odd number. Like this over that, and you get like 10 to the 9th, stuff like this. And so I don't know what goes on. So anyway, these are the answers to that problem right here. Problem 2. Now problem 3, go to test A again. Problem 3 was a short dipole. I think I telegraphed this one. I said you're going to get a short dipole. You have to know the short dipole, right? Have to know. So I simply said that I have an electric, I wanted to know I have a current, on the z-axis, at 1 gigahertz, 3 amp current, and its length is 1 centimeter. I thought this problem would be, everybody would get it perfect. Only thing I wanted was the electric field at the position shown at r equals 1 kilometer at 45 degrees. I just wanted the magnitude. It's 0.013. I wanted the average power. Now you're in free space, correct everyone? If you're in free space, average power is always 1/2 magnitude of the E field squared over eta. How many remember that? Because you remember it. All right, I know you guys remember, most of you remember. When you did the 1/2 real part of E time cross H conjugate, and you're trying to find H and then conjugate, you're wasting a lot of time. If it's in free space, take the magnitude of the E field, square it, divide by eta, divide by 2, and you're done. All right, that's the only thing I wanted. Now, the last thing was, and this is the one that was a little trickier, I wanted the actual total radiated power here. Now, you can get this 3 or 4 ways. Let me tell you one way. There's a radiation resistance for a short dipole that we covered in a couple of problems at least, and I talked about in class. The radiation resistance is 80 pi squared times the length over wavelength squared. All right, a lot of people had that down. And that means the power radiated was 1/2 times I squared, and you had to calculate I, right? It was given, 3, and square it, 9, times the radiation resistance, which is going to be 80 pi squared L over lambda squared. All right, you can get it that way. Another thing you can do is find the actual electric field at a given R and square that value and integrate it over 4 pi r squared. You can do it that way. Another thing you can do is use the solid angle, and people did this. They knew what the solid angle was, right? Times the power, maximum power density, power radiated at that range, right? And it was times, I believe it's r squared, and people had all sorts of things down for that. This is what I put down here. And one other thing, I don't know if I remember many people doing this for this problem, but you did it for the other problem, the next one. They also knew that the gain of that antenna was 1.5, right? The directivity or gain. So what they did is say, well, if I know that, then I know the power radiated, or the power density, PAV, would be power radiated. Let me just put this down right here so you can appreciate what I'm saying. All right, now what you knew is this. For a short dipole, you know the directivity was 1.5. And the gain is basically 1.5 times the sine squared of theta, because the sine squared of theta would be the normalized power, right? All right, now you knew that. So if you wanted the average power density, you knew that that was 1/2 magnitude of E squared over eta at that range, and you know what I'm talking about here, right? What does that actually equal to? Well, it's equal to the total power radiated over 4 pi r squared. That would be if it's an isotropic radiator, correct, class? Yeah. Then your gain would go here, and it would be equal to 1.5, right, times the sine squared of 45 degrees. And you could get the power radiated that way too. And people did it almost every which way you can imagine. But a lot of people would make mistakes because this is not 1. That right there at 45 degrees is 1 over the square root of 2. When you square it, it's 1 over 2. All right, just make sure if you're going to get P radiated using that formula, you use the right, you include the sine squared of theta, because it wasn't at 90 degrees. That's the thing. Are you with me on this, everyone? Just be careful about this. All right. That was on test A. Test B, these are the answers for test B, but it's, what do we have here? F was 2 gigahertz, so the frequency changed. And I think that was it. And these are the values for the E field, for the average power, and P radiated. And you can get that stuff any way you want. I saw a lot of stuff I didn't quite know what you're doing, and you may not have known what you were doing, but I saw things down there that I was really uncertain of what you were trying to do, if anything. This was not a hard problem. This was meant to be something that you've seen several times in the homeworks. Lastly, Last problem was the half-wave dipole, and there's a lot of ways to do this. For the half-wave dipole, because I was concerned, and I said you weren't responsible for memorizing the E field from that, I gave you the E field, all right? I gave you the E field. On top of that, I gave you the antenna's impedance, 73.2 plus J, 42.5. And then I gave you a voltage source, right? I gave you a voltage of 50 volts in this one, right? So the first thing you had to do is get the current, right? And for the current, oops. The current here was just V over Z antenna. That's all it is, correct? Yeah.
In the question it says the voltage is 100, the picture had 50.
If you use the wrong voltage, I mean, if you use the if you got confused on that, bring it to me. I'll give you credit. All right? If you have any questions, I will credit you if it's a mistake. This test irritated me to no end. I tried printing it out 5 times. I had to do 5 or 6 different iterations. It finally printed. I have no idea why, other than sometimes printers, they get software updates to these things that just cause problems. And maybe my OneNote wasn't updated to whatever the software is up there. But anyway, it was driving me bananas to try to print this thing out. And so I'll give you credit if it's a mistake on my part. Now, this one's straightforward. Just listen to me now with the method. You have the antenna impedance. You need the antenna current. You divide the voltage that's driving it by the antenna impedance to get the current, right? Now, once you have the current, please listen. This is important. Once you have the current, you can do one of 2 things. I gave you the E field up here, the equation for the E field, right? I'm trying to get this thing to, let's see if I can get it. Y'all see that equation for the E field right there? You can just plug that in and get the E field, right? I gave that to you for that reason. That's one thing. Or you can do what I did, and a lot of you, in fairness, I'm not sure how many did this. Because I was grading this thing, and I'd stop, and I'd go back and regrade, try to see, are they really doing that? But another thing you can do, and I'll just tell you, because a lot of people saw this, they saw that the real part's 73 ohms, right? 73.2. I know the radiated power is just 1/2 that resistance, the antenna resistance, times I squared, right? Magnitude of I squared, right? That's the total radiated power. Follow me? Once you have the total radiated power, if you want the actual power density anywhere, I mean, you didn't have to do it this way. You can just use the E field equation, all right? You didn't, but this is straightforward to me. Once I have P rad, the next thing I want is the average power density at a given point. And I can say that's equal to P rad, right? Divided by 4 pi r squared. That's as if it's an isotropic radiator, right? Times the gain of the antenna. That was a half-wave dipole. This is the one we did cover in class and mentioned several times. This has a max gain of 1.64, right? Y'all remember going through this? That was the dipole's 1.5. The half wave is 1.64, and then everything else you have to calculate. You had problems on this, several. Now that's that, and you know that there would be times f of theta, but there I asked at 90 degrees, right? Correct, class? So at 90, that's 1, and that's something we covered in class. So that'll give you the average power density at that point, and the average power density is equal to 1/2 magnitude of the E field squared over eta, right? So you can get the E field. I think I did it that way here. Therefore, if I want the E field, it's 2 eta naught times P av, and that would be the incident E field at the target. Does everybody follow me on this? Now, you don't have to do it that way. You could actually do it this way. Just plug in the value of current there, and you'll get the same exact value. But I'm showing you an alternate way to make sure you do understand this. In the future, I would suggest you work from the power point of view. But this, I gave you that so you could get it directly from that. And I think I do it down here. I've got that one. Yeah, I'll show you that in a second. Anyway, once I have that in E field, now I need the reflection coefficient out here, right? The reflection coefficient is eta 2 minus eta 1 over eta 2 plus eta 1. I knew that eta 2, because the actual epsilon relative is 12, the impedance would be the square root, because it's lossless, of mu naught over 12 epsilon naught square root of that. Or really, it's just 120 pi over the square root of 12. Follow me? So once I had that, then I got the reflection coefficient. Right here, that's just magnitude, it'd be negative. Then I got the transmission coefficient, 1 plus reflection. Then I take the transmission coefficient times the incident field to get the transmitted electric field. And once I have the transmitted electric field, I divide that by eta 2 to get the transmitted magnetic field. That was the process. And I think a lot of people got this value by simply taking the E field here divided by eta naught times tau. They didn't actually calculate the E field in the media if it's transmitted and then divided by eta naught, or eta 2. So it's just not transmission coefficient times the H field incident. You have to get the incident field first, the incident E field, multiply it by the transmission coefficient, get the transmitted field, and then divide that transmitted field by eta 2. It's the impedance in the media. Everybody follow me on that? All right, that's problem A, and those are the answers, and I'll make sure you have all these answers. For part B, these are the answers for part B. One thing was changed, right? It was 100 volt there, right? Follow me? And that was the whole test in a nutshell. I think a lot of the calculations, I'm not actually sure. I saw people working really feverishly, and I wasn't sure. You said problem 2 took a long time?
So it was just asking for a lot of things.
But one thing usually led to the next, right? I mean, if you... Well, I mean, you didn't have to do it that way, but I tried to set this up like the homeworks. This particular problem, like the first problem here, where you're taking this and you got two media, you know what you're going to do is calculate eta 1 and eta 2 of the two different media. Have to get that. Then you get reflection coefficient, transmission coefficient. This is sequential, regardless of what's asked for. After you get that, if you want, you get transmitted, reflected, and incident field, right? You get all those things for E or H. Anything else you want, power and stuff like this, it's just using that, but it's methodical. It's going right down the thing. The minute you've got two different media, you're looking at first characteristic impedance. After that, you're looking at, if you take a look at this, after that, you're looking at incident field, transmitted field, E field, and reflected field. After that, if you want power, you've got it, or H field, yeah.
In the future, would you consider an equation sheet, or should we just program like equations to a calculator?
Well, I don't allow equations. This is not stuff that's very complicated to remember. This is pretty straightforward stuff.
The amount of equations we needed for this one is pretty, yeah.
What was that?
Expensive. The amount of equations that we needed for the test is pretty expensive.
Well, the one I gave you, I gave you the one for the waveguide, right?
Yeah, it's just I'm saying the amount of equations we needed for this test is pretty expensive. So would we, in the future, could we do one, or just program all of it to a calculator?
Well, I'll give you tell me what equations you want, and I'll see if they're justified. I mean, when I say 1/2 E squared over eta, that one is kind of a gimme, and then current is V over Z is kind of a gimme. You show me what you want, and I'll be happy to consider it, all right? I mean, anything complicated. I didn't give you any kind of oblique reflection stuff. I know that stuff takes a while. I didn't even get a Snell's law on here. I was going to put a fifth problem on. I'm glad I didn't. I didn't give you a lot of the stuff that usually shows up in this first test. But I am going to tell you one thing. If working your calculators is the rate limiting step here, please spend some time learning how to do, especially that calculation I had up here, because that's the one that blew me away. So many people had it wrong. I mean, in a big way. They had the right equation, right numbers, wrong answer. It's like, how? Yeah. I can't hear. Yeah, I'm going to put both solutions up on one now. And if you download MathCAD, you can do the equations my way. It takes a little, there's a few tricks with MathCAD, but it's very, to me, it's extremely easy to use. And the reason I like it, what I see is what I get. And the minute I change one thing, it changes everything. So I can go ahead and play with that all I want. And I don't know how much the actual full version is. I have access to it, but it's through a FlexLM license. Now, if you have questions, hear me now. I have another class, but I'll be available after 2 o'clock, and I'll be happy to answer any questions that you have.
Do you, like, whenever
2
you
o'clock
ask
today,
for
yeah?
questions, do you, like, want magnitude unless, like, you say...
Unless I say I want the entire expression, you just, because this is the way it is in the real world. We want magnitude, that's what you measure. The only reason phase comes into play is with radar and stuff like that. The phase difference in 2 signals plays a role in figuring the actual incident angle and things like this. All the stuff I am going to ask you for is pertinent to really, in the real world, what you use and why you use it. And these problems are based on real world problems, stuff you're going to see. Now, one last thing. If you blew it, for whatever reason, Mississippi State or whatever, there's still plenty of time, all right? You can do the math on this one. This is 25% with that 10-point curve of your final grade. Just do the math on this. Most of your grade is way out there in the future, all right? You got another test, the final. Next test is 25, final is 30. All your quizzes are 20, all right? Just do the math on this. You can recover. You can get an A still, all right? But you got to stay with me on this stuff, and please keep up with the homework. And yes, I will give you homework with numbers and more of it, all right? Let me finish one thing. The next thing I'm going to cover, if you want to read ahead, if you finally got paranoid, then the Friese transmission equation and radar is where I'm going. This is going to be the next lecture. We are not having a quiz on Friday, if that's your question, all right? Because that would be a natural thing. You're not going to get a quiz on Friday. Friday, I'm going to cover this stuff. Please show up, because some things in the radar in our book are a little different. Wentworth does a really good job with the basic explanations, but there's some things that are lacking. Yes? Anything else?
You heard at the end of the course.
I couldn't hear what?
You heard at the end of the course.
What?
You heard at the end of the
So
course.
like, did you already add in the 10 points, or will that be at the end?
The 10 points is on this test. All right, if you made a 40, if you made a 30, you made a 40 out of 40. Got me? So it's really, when you think about it, it's 22.1.
125.